Let's go ahead and get started. Okay, so today we're going to continue with our discussion of chaos. So let me just remind you of a few things that we discussed last class. So we imagined starting with a system which is integrable and is given by a Hamiltonian H naught, which is integrable, and adding to it a perturbation which is proportional to some parameter epsilon, such that the system for non-zero values of epsilon becomes non-integrable. And my claim was that for sufficiently large values of epsilon, many such systems become chaotic, and we would like to study chaos by understanding the onset of chaos at a particular critical value of this parameter epsilon. And just to remind you, what do I mean by a chaotic system? Well, I mean a system whose trajectories exhibit four rather counterintuitive properties. So the first property was the property of mixing, which is that if you have two regions of phase space, then a trajectory which starts in one region will eventually end up in the other region, and this is true for any two regions, so that there's no sort of separation between trajectories that live in one part of phase space as opposed to a different part of phase space. The trajectories will also be dense in the sense that any trajectory will approach every point in space-time to an arbitrary degree of accuracy, even though it may never arrive at exactly at this point in phase space. It will approach it to an arbitrary degree of accuracy. And moreover, the trajectories will be quasi-periodic in the sense that they approach every point on phase space an infinite number of times. So they are periodic in the sense that they repeat themselves by approaching every point on phase space an infinite number of times, but they're only quasi-periodic in that they do not do so with any definite interval. And finally, they are sensitive to initial conditions. And the sensitivity to initial conditions is quantified by a parameter called the Liapunov exponent, which says that the distance between points in phase space will, for very nearby points, grow like e to the lambda t, where lambda is the parameter with dimensions of inverse time that sets the time scale for chaotic behavior in the system. And as we'll see, the statement that the chaotic trajectories are dense is quantified by what we call the fractal dimension of the trajectory. So we considered a variety of different chaotic systems, and we settled on the following very simple model of a chaotic system, which is given by the logistic equation. So in order to have a calculable model of chaotic behavior, we considered a discrete system where time is replaced by a discrete variable, and our variable x will evolve according to a second-order equation that is parameterized by this parameter a. So remember that chaotic behavior occurs only in systems where you have some nonlinearity, And this logistic equation is the simplest possible evolution, which is nonlinear. Namely, it's quadratic. And then we understood that the evolution is stable for a less than, I guess, a value that we could call a naught, which was equal to 3. So you imagine increasing a, and then as a hits 3, suddenly the endpoint of the system where this logistic equation has a fixed point became unstable. And for a greater than a naught, but less than a value that we could call a1, there in fact were two stable endpoints, which oscillated back and forth between one another. And for a bigger than a1, but less than a2, we had 4 endpoints, and so on and so forth. And finally, at a infinity, as a approaches a finite value of a that we called a infinity, we have an infinite number of endpoints, and beyond this value of a, the system became chaotic. So, if you wanted to draw a graph of the possible endpoints of the system as a function of a, then for a less than 3, there would be a single value. And then as a becomes greater than 3, there will be 2 possible endpoints, with the property that if you start with x at one of these values and then evolve forward, you'll end up at the other value, and so they'll switch. And so we have what's known as a bifurcation. And then at a1, we have another bifurcation, and then at a2, another bifurcation, and so on and so forth. And the remarkable thing, well, there are a variety of remarkable things about this graph, but the remarkable thing is that the bifurcations occur more and more quickly as a function of a, and so that we have an infinite number of bifurcations at a finite value of a. And a infinity is not so hard to compute in this system. It has a numerical value of a little less than 3.57. And so, beyond this value of a infinity, the system is chaotic. And so what we would like to try and do today is characterize this approach to chaotic behavior as a approaches a infinity. And in fact, there are a lot of very remarkable features of this system. So, any questions before we continue? Everyone remembers more or less where we left off last time? Yes?
So, beyond a infinity, does that mean that the equation has no stable endpoints? Or
that's correct. Well, it has an infinite. Well, the answer is yes. It has no stable. What's that?
Oh, isn't it a yes or no question?
Well, but in fact, the two alternatives that you presented to me were the same thing. The statement that it has an infinite number of stable endpoints is the same as the statement that there are no stable endpoints. You see what I mean by that? Okay. It only makes sense to talk about a stable endpoint if after a finite number of steps you return to that point. So, for example, at this point here, we have one stable endpoint, and at this point here we have 2 which alternate between one another, and then here we have 4 which permute among one another, and so on and so forth. But if you have an infinite number, there's no sense in which they permute among one another because it would require an infinite number of steps. So there's really no stable, there's no stable endpoint. And in fact, there was a question?
I don't know if it was this or not, but once you enter into chaotic behavior, is there a certain region of chaotic behavior that becomes
more or less what?
More or less it has patterns to read?
Yes. I'm going to discuss in much more detail exactly what sort of patterns this structure exhibits. So one just maybe to answer your question right away, one remarkable feature of this system is that for values above a infinity, the system becomes chaotic. But as you keep increasing a, at some point it stops being chaotic. And in fact, this region of chaos is finite. And then for a larger value of a, there's another stable point. And then it bifurcates. And then there's another region of chaos. And then it stops again. And in fact, there's an infinite number of regions of chaos and non-chaos within this region here. So in fact, there are an infinite number. There are regions of non-chaotic behavior embedded inside the regions of chaotic behavior. And that can be quantified, actually. So this, for example, would be a non-chaotic region which is embedded inside the regime of chaotic behavior. I actually lied a little bit when I drew this diagram, which you can see if you think about it. Because in fact, you have an infinite set of bifurcations on both sides. Because the only way that you approach chaos is by having this type of bifurcation. And so, in fact, you have this bifurcating structure on both sides of the regions of chaos. So whenever you approach a chaotic point, you have a point where there's an infinite amount of an infinite number of stable points. You have an infinite number of fixed points developing, and so there are, in fact, an infinite number of such non-chaotic regions embedded inside this chaotic region. So if you wanted to quantify that, you could actually graph this Liapunov exponent as a function of the value of a. So here, when I mean a Liapunov exponent, I mean the Liapunov exponent averaged over all possible initial starting values between 0 and 1. And what does it mean for the system to be stable? So if this is the line, well, let's write it here. So if this is lambda equals 0, then the system is stable if lambda is negative. And it's unstable if lambda is positive. And so, in fact, for values less than 3, there is a 0 at the first of these bifurcation points. And then, in fact, lambda goes to negative infinity. And then it comes up in the chaotic region, and that goes to negative infinity again. Then it comes up higher, and then it goes to negative infinity again, and it higher, and it sort of fluctuates like this. And so, in fact, as you go up to a equals 4, so remember a had to be between 0 and 4 in order for the evolution to be well defined on the interval where x lives between 0 and 1. And so, in fact, there are an infinite number of stable regions embedded in the chaotic regime where a is between a infinity and 4. But the sizes of these chaotic regions gets narrower and narrower and narrower. The sizes of these non-chaotic regions gets narrower and narrower and narrower. So there are several other kind of fascinating properties of this system. One of the most remarkable properties is that, in fact, this picture of the bifurcating diagram at the approach to chaos is, in fact, a fractal in a precise sense, which I will make quantitative in a minute. But if you just look at the picture that I've drawn here, so if this is the onset of chaos here, then, and you have this infinite set of bifurcations, then it turns out that if you zoomed in on one of these bifurcating regions, and you looked at what that plot looked like, then you would have exactly the same plot. And then if you zoomed in again on this region over here, you would have exactly the same plot again. And so on and so forth. And so there's this self-similar structure, or recursive structure, that is a characteristic of a fractal. And this is one of the things that characterizes chaotic systems, this fractal behavior. And in fact, there turns out to be a rather remarkable way that one can characterize this fractal behavior. So it turns out that, as we said, the value of A0 here was equal to 3. This value of A1 was around what? 3.4. This was around 3.5, 3.55, and so on and so forth as we approach A infinity, which was 3.5699. And because this system is self-similar, it actually means that the ratio of distances between the successive values of an approaches a constant. So if you write an minus an plus minus 1 over an plus 1 minus an, so the ratio, say, between this distance here and this distance here, you could calculate that ratio, it's a number. And then you could calculate it for the next step, the ratio between this distance here and that distance there. And then you could imagine taking the limit where n goes to infinity. And it turns out that it approaches a constant, which is about 4.669. So what does that mean? That means that in order to obtain this self-similar structure, I rescale by an amount 4.669 each time. I rescale the axes of my diagram by an amount 4.669. And this number, 4.669, is actually kind of special. It's known as Feigenbaum's constant. And it's a fundamental constant of mathematics, just like pi, e, square root of 2, or so forth. And in fact, every chaotic system, which is described by a first-order evolution in terms of a first-order equation which is quadratic, will exhibit precisely the same approach to chaotic behavior, characterized by the same value of delta. So anytime you have an approach to chaos that is governed by a linear differential equation, or a linear iterative equation as we have here, provided the right-hand side is quadratic, then the approach to chaos will always be described by a self-similar structure, where I rescale by a factor 4.669 each time. And of course it's not 4.669. It's 4.669 ... Well, nobody actually knows if the number is irrational or not. I mean, we all know that e and pi are irrational. It's not known whether Feigenbaum's constant is irrational. But it's a universal constant of nature which describes the approach to chaos in this very simple class of systems. Yes? Well, I've given you a algorithm for computing this number, because I told you how to compute A0, A1, A2, and so forth. So in principle, you have an algorithm for computing this number, but that algorithm involved finding lots of roots of high-order polynomial equations. So in practice, you wouldn't be able to do this explicitly, so it can only be done numerically.
If it can only be done numerically, how do you know for picture systems?
well, you compute it. And, well, actually, you could probably, I think Feigenbaum proved that it's the same. I think he proved that it's the same for any logistic equation, quadratic logistic equation. So I think it's possible to actually prove that it's the same. That's a good question, though. I mean, in principle, I've given you all the information that you need to write a computer program to compute Feigenbaum's constant. And I think the remarkable thing is that, even though, when we say the word chaos, we think that there's no structure there whatsoever. But what we discovered is that the approach to chaos, in fact, has a lot of structure, and that for any linear system, for any first-order differential equation which has a quadratic nonlinearity, the approach to chaos is described by the exact same scaling. It's a rescaling by this particular constant, delta, which is a fundamental constant of nature or of mathematics, the same way that pi is, or something like that. So there's another constant which characterizes, I'll have to look it up. There's another constant which characterizes the approach to chaos here, which is the dimension of the fractal set. So you can look at the set. So if you look at, for example, A1, you have this bifurcation point where you have a single point that's bifurcating. At A2, you have 2 points that are bifurcating. At A3, you have 4 points that are bifurcating, and so on and so forth, until you get at A infinity to an infinite number of points that live on this line. And so the set of x infinities at A equals A infinity is what is known as a fractal set. And it has dimension that's given by 0.538. Well, that also is 0.538 ... So normally you're not used to thinking of geometric objects with a dimension that is not an integer. And so what I would like to do now is describe what it means for a set to have fractional dimension. Are there any questions on that before I continue? Have you guys seen this before, maybe in your math classes? Okay. So what does it mean for a set to have fractional dimension? Well, in order to understand that, we need to understand what dimension is. So when I say that a point is zero-dimensional, a line is one-dimensional, a surface is two-dimensional, and so forth, what precisely do I mean? Well, imagine we have some sort of shape or a set of points on a plane. So we have a plane given by this blackboard or this projector behind me. And we have some set of points on the plane. And imagine that we just have some shape, a point, a line, a circle, a square, some shaded box or something like that. Then how could I determine the dimension of that? Well, what you do is you imagine taking this shape or more precisely, what you imagine doing is dividing the plane into little squares of length epsilon, where epsilon is a very small number. And then you denote by n of epsilon the number of squares occupied by this shape. For example, let's say that we have a curve here. And then we imagine this curve on the plane, and we imagine dividing this plane into lots of little small squares. Then we would count up the number of little squares that overlap this line. And what does it mean for the line to be one-dimensional? It means that the number of squares will grow like epsilon, 1 over epsilon, in the limit where epsilon is small. And what would it mean for a two-dimensional shape? Well, for a two-dimensional shape, the number of squares would grow like 1 over epsilon squared in the limit where epsilon goes to 0. So the number of squares that are occupied by this shape should grow like epsilon to the 1 over epsilon to the dimension of the shape. Okay, for small epsilon. Okay, this is nothing more than the statement that the length of a line is proportional to the length of a line, or rather, but the area of a square goes like the length of the side squared, or the volume of a cube goes like the length of a side cubed, and so on and so forth. This is nothing more than a slightly formal way of restating that. Is that clear? Is this statement clear? Okay. So let's now look at that equation and solve for the dimension. Well, you take the logarithm of both sides, you divide by the log of 1 over epsilon, and you see that the dimension is equal to the log of the number of squares over the log of 1 over epsilon. And we don't want to take into account any errors that we might make because these boxes have finite size, so we can take the limit where epsilon goes to 0. Oh, I'm sorry. Why did I take the log there? I'm taking the log because this is 1 over epsilon to the dimension power. So you take the log of both sides. You get the log of n is equal to the dimension times the log of 1 over epsilon. We divide both sides by the log of 1 over epsilon, and we have the dimension. And now all we need to do is take this definition seriously. And we'll see that for normal sorts of shapes, this answer is an integer, 1, 2, 3, whatever, like you would expect. But for other more complicated sorts of shapes, such as those that are the trajectories of chaotic systems, this number is not an integer and is a fraction. So this notion of dimension, in mathematics, there are a variety of notions of what you could mean by a dimension of a set. There's things that people call the topological dimension, the fractal dimension, the Hausdorff dimension, and so on. This is roughly the Hausdorff dimension from the mathematical point of view. And there's one important point that I should make here, which is that I used the word square in defining this notion of dimension, because I divided everything into squares. I could have also used triangles, or circles, or hexagons, or anything like that. Any shape. And the answer that you get for the dimension at the end of the day won't depend on what sort of shape you use to divide up space into very small little bits. So the answer that you get is only the log of the number of shapes that it takes to cover your object over the linear size of a shape. And in fact, I certainly won't prove it to you. This answer that you get at the end of the day will not depend on what sort of shape you use, provided you don't do something truly perverse like try and use a fractal shape or something like that. Okay. So what would be an example of a shape which would have a non-integer dimension? Well, let me give you a very simple example, which is something that's known as the Cantor set. Cantor was a smart guy. He's the person who was responsible for observing that there are different kinds of infinity in the world, and that the infinity of real numbers is much greater than the infinity of integers or natural numbers. And he also gave us what I think is probably the simplest example of a shape which has a non-integer dimension. So have any of you seen the Cantor set before? Okay. So let me define for you the Cantor set. So it's a shape with non-integer dimension. And it's a very simple shape. It's a shape that lives on the real line rather than on a plane, although I'll draw for you higher to plane analogs in a minute. But it's defined as follows. Take the set of all points between 0 and 1. And then remove the middle third of this set of points. So this would be, then we have the set of all points whose value is between 0 and a third and 2/3 and 1. Okay. Then take each one of those regions and remove the middle third. And we end up with 4 regions with values between 0 and a ninth, 2/9 and a third, 2/3 and 7/9 and 8/9 and 1. And now keep doing this forever. So define the set, say, S0 is the interval between 0 and 1. S1 is the thing with all the inner thirds removed. S2 as S1 with all of the inner thirds removed. S3 as the set with the inner thirds of S2 removed, and so on and so forth. Then what are you left with at the end of the day? So S infinity would be the thing that you get as an end result of all of this. You know, if you wanted to use some fancy math lingo, you would say that S infinity is the intersection of S0 with S1, with S2, and so on and so forth. Where that little upside down U is the symbol for intersection in mathematics. But that's not terribly important. So first of all, what is the volume of this set? Well, the volume of S0 is 1. And then because we remove the middle third, the volume of S1 is 2/3 of that. The volume of S2 is 2/3 of that, which is 2/3 squared. And so the volume of S infinity will be 2/3 to the infinite power, which is 0. Each time we do this, we reduce the volume by a factor of 2/3. 2/3 is less than 1, so if you keep taking its powers, its volume is 0. So it's a set of points on the line whose volume is 0. So you would be perfectly justified in thinking that it had dimension 0. But you would be wrong. Well, there is a sense in which it has dimension 0, but there's just as equal a sense in which it has a dimension that is not 0. So let's go ahead and compute its dimension. Are there any questions on this before I continue? Is this construction clear? More or less? Is this construction unclear? Yes. No, there's nothing magical about a third. Do this with 1 over n. Well, yes, the dimension will be different. In a minute, you'll see, it'll be clear to you how to compute the dimension of this set for any value, if I did a quarter or a fifth or whatever. Okay. So, in fact, this construction tells us exactly what the dimension of the set is. So let's imagine dividing the real line into squares, where here I just mean little lines of length epsilon, which is 1 over 3 to the n. That's what I'm doing here. In this first step, I have a line of length 1. The second step, I have 3 lines of length 1/3, of which only 2 are occupied by my Cantor set. Here, I have 9 lines of length 1/9, only 4 of whom are occupied by my Cantor set. And continuing in this way, you see that in this case, the Cantor set occupies 2 to the n of these line segments. So the dimension is the limit, where n goes to infinity, of the log of the number of such line segments which are occupied by the Cantor set, 2 to the n, divided by the log of the inverse size of those line segments, which is 3 to the n. And happily, when you take the logarithms, those n's cancel out, so this is n log 2 over n log 3, which is log 2 over log 3, which as a number is around 0.6. So you can see that you can characterize the behavior of this set by a fractal dimension. And this is precisely the sense in which the chaotic logistic equation has a fractal dimension. And it was a fractal dimension of around 0.5 something, as I quoted for you earlier. What was it? It was 0.538. And it turns out that a fractional dimension is the characteristic feature of a strange attractor, or it's the characteristic feature of a chaotic trajectory. And you can parameterize the degree of chaoticness of a trajectory by its dimension. And so it's an amusing thing to do to compute this fractal dimension for all sorts of other interesting configurations. So let me just give you an example. So for example, consider, just as another sort of abstract mathematical example, consider the set of all real numbers, which when you write out the decimal expansion for the real numbers, you only have even digits. Well, this is dense in the set of real numbers because every real number can be approximated to, well, that's not quite true. Okay, not every real number, but a lot of real numbers can be approximated by real numbers with only even digits. So does anyone have a guess for what the fractal dimension of the set of all real numbers with only even digits is? I'll give you a hint. What's that? I'll give you a hint. Let's think about the Cantor set. And let's imagine taking a point on a real number and writing it base 3 and seeing what that means for the Cantor set. Well, it turns out that what this means for the Cantor set is that in base 3, you only have zeros and twos, but not ones appearing in the base 3 expansion of a real number. That's what it means to remove this interior third region. So another way of saying what the Cantor set is, it's the set of all real numbers written in base 3 which don't contain a 1. Only zeros and twos. And so, similarly, we could write down the set of all real numbers with even digits, and the dimension is log 5, the number of even digits, over log 10, the number of digits. And so that is between 0 and 1. You can also come up with higher dimensional examples. So, for example, there are something known as the Sierpinski gasket. So you can imagine taking a triangle and considering all the points in that triangle, and then removing this inner triangle. And so you've got 3 triangles left, and then remove the inner triangle of each one of those. So then you have 9 triangles, and then you remove the inner third of each one of those, and so on and so forth. So this is also an example of a set with fractional dimension. And here the dimension is larger than 1, and it's equal to log 3 over log 2. Why is that? Well, for each triangle, we're dividing it into 4 regions and throwing out one of them. So we're keeping 3 out of the total of 4 regions. And you could think of 4 as being the area of that triangle, which has linear size 2. The area being proportional to base times height. And so this is larger than 1, but less than 2. Now, I couldn't resist going to Wikipedia and looking up other examples of sets with fractional dimensions. So if one relaxes our definition of the fractional dimension just a tiny bit and says we don't have to take epsilon to be 0, but we just have to take it to be very small, then there are lots of real-life objects which have a fractional dimension. So, for example, Norway has a coast which is very crinkly, right? It has lots of divots and turns and stuff like that. And so if you look at a small but non-zero length scale, you can actually compute the dimension of the coast of Norway. And it's actually very close to that of the Sierpinski gasket. I wonder if that's probably an accident. And whereas other countries with coasts that are less crinkly have coastlines whose dimension is much closer to 1. So, for example, the famous example of a country with a very straight coastline was given by Mandelbrot in one of his first papers on fractals, and that's about 1.02, very close to 1. Another example of a familiar shape with a fractal dimension on a particular length scale is a cauliflower. So if you've ever closely investigated a cauliflower before eating it, you may remember that, in fact, there's a sort of recursive structure in the leaf, I guess you call them leaves of a cauliflower. And in fact, there are 13 little protuberances organized in sets of 3. And so the dimension of a cauliflower, well, it's an object in 3-dimensional space. And so you would guess that its dimension is larger than 2, but less than 3. And in fact, it's about 2.88. So, if one is particularly generous in your definition of dimension, then you can assign a fractional dimension to all sorts of objects, and they quantify the sense in which an object has a recursive structure that is dense but does not completely fill the space that you're thinking about. And it's this fractal structure which is characteristic of chaotic orbits. Are there any questions on that? Yes.
So if you take epsilon equal to 0 for those, then we get the right version.
Yeah, of course. Of course. In all of these, I'm taking epsilon to be small but not 0. On the distance scales of a person, the coast of Norway looks quite straight, I'm sure, to Norwegians. But from the point of view of someone looking from a satellite from above, it looks quite crinkly. And so one needs to have... So you can actually just talk about a dimension as a function of length scale. And here, I'm choosing a length scale so that I can give you an impressive-looking number. That's far from an integer. But on very small length scales, yeah. Yes?
So it's not a limit.
Yeah. Well, really, strictly speaking, when I say dimension, I mean the limit. I mean, if you talk to a mathematician, that's what they would say. But, you know, we're not mathematicians.
But if you're not in the limit, how do you get the number? What will stop?
Well, yeah, I'm just choosing a scale to give me an interesting result. I mean, obviously, the dimension of the coast of Norway is really equal to 1 because it's a line. But if I work at long-distance scales, scales of a kilometer or a few kilometers or 10 kilometers, then it's actually quite crinkly. And that's the distance scale that I'm working at in order to get this answer. If you look at, yeah, go ahead.
Like, if you were to look at one of the more famous fractals, like the Mandelbrot set or something, the full dimension out of that.
Yes. Yeah, I mean, that's why this is called a fractal dimension, is that every famous fractal that you've heard of has a fractal dimension, by and large. Questions? Other questions? So, you know, so far I've told you a lot of qualitative features of chaotic systems. And I would like to end by asking one additional question, which is whether we can say anything precise, anything else precise about the onset of chaos. So remember that we're thinking about a chaotic system as a system which has a Hamiltonian that varies as we vary a small parameter. And I could literally imagine doing this physically and having a driven pendulum, say, which is driven with a particular driving force, and turning a dial so that that driving force depends on time. So you could ask the question, what happens if we change the parameters in the Lagrangian or the Hamiltonian very slowly with time? So, for example, you could imagine starting with a system that is integrable and non-chaotic, and adding a small perturbation which renders the system chaotic. And you could imagine very slowly changing a dial on your experimental apparatus so that as a function of time, this Hamiltonian gradually transitions from non-chaotic to chaotic. And so you could imagine that because the initial system was integrable and completely solvable, you might be able to use this to say something about the non-chaotic system. And in order to do so, you would have to ask the question whether anything remains constant as I change the value of epsilon. And if you like, you could imagine changing epsilon very, very, very slowly in order to see if anything remains constant. And it turns out that there are certain quantities which do remain constant as you dial a parameter in the Hamiltonian or the Lagrangian as a function of time that takes you from integrable to non-chaotic to chaotic behavior. And such quantities are known as adiabatic invariants. And in fact, the subject of adiabatic invariants not only plays a role in the theory of chaotic systems, but it also played a very important role in the history of the development of quantum mechanics, which I'll spend a minute describing at the end. And in fact, these adiabatic invariants are quantities that we have already met in this class. We just did not know that they were adiabatic invariants. So let's consider a one-dimensional system, say, whose Hamiltonian depends on P and Q in some very arbitrary way given by some potential V that depends on Q. So if you wanted to solve for the motion of the system, the first thing that you would do is you would draw the curves of constant energy on the QP plane. And it turns out that if you imagine that this potential depends on a bunch of parameters, say the frequency of the oscillator or something like that, and you imagine changing those parameters very slowly in time, then the quantity which remains constant is in fact the area inside a curve of constant energy. And this is nothing more, nothing less than the action variable which we considered in our study of integrable systems. So this action variable remains constant in time. And in fact, there are a variety of ways of seeing that this remains constant in time. The hard way is to do the straightforward computation where you imagine including some time dependence in your Hamiltonian, computing the time variation of I, and then taking the limit where this time variation is very slow. But in fact, there's also a zero-line proof of this statement, which can be understood very intuitively. And the proof is just to use Liouville's theorem. Liouville's first theorem, not his second one involving integrable systems. So what does Liouville's theorem say? Liouville's theorem says that if you take a blob in phase space and you evolve it in time, then its area remains unchanged. So, for example, if at early times you consider the blob, which is made up of all trajectories with energy less than a value E naught, then as you evolve in time, the shape of that blob might change. You know, maybe it looks something like that, but the area remains constant, and hence this action variable remains constant. There is, however, an important subtlety when I make this argument, which is that although the area of the blob remains constant, even though at initial times it was a surface described by trajectories of bounded energy less than some value E naught, at late times it might not necessarily have that form. And the reason, roughly speaking, is that you could imagine that you have some trajectories which are all going around this circle of constant energy, and then after you evolve forward a very long time, those might not all end up on the same surface of constant energy. In order to get around that, you need the scale of the time variation to be very long compared to the period that it takes one of these particles to move around in orbit. So what you need to do is you need to take the time variation of the parameter in your Hamiltonian to be long compared to the period. So that means that if you think about it, the collection of trajectories which move around a surface of constant energy in the far past will continue moving around a surface of constant energy in the far future. So that the action variable will really be unchanged as a function of time. And so a small change with this property that it varies on long timescales compared to the period of an oscillation is known as adiabatic. And in fact, the theory of adiabatic transformations also appears in thermodynamics. You might have studied adiabatic processes in your thermodynamics class. They're precisely those processes where entropy is not created. And in fact, that is for very similar regions. And as I promised, in fact, the theory of adiabatic invariants plays a very important role in the historical development of quantum mechanics. And I would like to now explain to you why that is the case. So let's imagine the following. So let's imagine that I have my favorite mechanical system, which is a pendulum. And we could even imagine that the length of the pendulum is very long compared to its fluctuations, so that it's effectively a harmonic oscillator. And we could imagine doing the following. We could imagine that we're sitting up here at the top, and that very, very slowly we let out more and more rope so that the length of this pendulum increases. And if we do this sufficiently slowly, then the quantity which remains fixed will be the action variable. So, for example, if we have a harmonic oscillator, so let's just take the mass of the object to be 1, and we'll take the length to be very long, so that the energy is omega 1/2 p squared plus omega squared q squared, then it's easy to compute the area contained inside a surface of constant energy. So let's go ahead and do that computation. So the area inside a surface of constant energy, well, let's forget about that 1/2 there. That's not going to matter too much at the end of the day. So the area, and that's the advantage of doing the optional part at the end of the class. Nobody will complain if I forget a factor of 2. So the curves of constant energy are these ellipses, and if the vertical axis of the ellipse has length p naught, then the horizontal axis will have length p naught over omega, just because this point here has energy p naught squared, and so this point here will have to have q, which is p naught squared over omega squared, in order for the energy to be constant. And here, p naught is related to the energy by p naught squared is equal to E, and the area, which is the adiabatic invariant, is given by the area of an ellipse, which is pi times the product of the minor and major axes. So that's p naught squared over omega, or E over omega. So what does that mean? That means that if you take a simple harmonic oscillator and you vary omega as a function of time very slowly, then the energy will vary as well, and it'll vary in such a way that E over omega stays constant. So if you take a pendulum, which is oscillating with a particular period of 1 second, and you let out the length of the pendulum so that the period changes by a factor of 2, then the energy will have to change by a factor of 2 as well, in such a way that the energy over frequency is constant. Now, what does this have to do with quantum mechanics? Well, you may remember, as we've discussed a few times in this class, that the basic slogan in quantum mechanics is that the action variable is quantized. For, in particular, the area in phase space is integrally quantized in units of h bar. For example, in the case of the simple harmonic oscillator, you remember that the spectrum of the harmonic oscillator is given by h bar omega times an integer plus a little quantum correction. And so, you could then imagine doing the following experiment. You could take a quantum mechanical oscillator, and you could imagine very slowly changing its frequency, and asking how the state of the system varies. And that's all well and good classically, but quantum mechanically, we know that the energy has to be an integer times omega. And an integer is a discrete variable, and so it can't depend, you can't have an integer which is a continuous function of a continuous parameter. It makes no sense for an integer to depend continuously on time. So you can't have n which depends continuously on time. And so that perplexed people in the beginning days of quantum mechanics, who said, well, if I have a quantum mechanical oscillator which is in a state given by E as h bar omega times an integer, then if I vary omega, then it seems confusing that I would need to vary the state that I'm in, given by an integer n, in a way to reflect this. And the resolution of this puzzle was observed by Einstein, who pointed out that when you vary the system very slowly, the quantity that remains constant under an adiabatic variation is precisely the thing that's quantized. And that's consistent with the statement that you can't have an integer depending on a continuous variable. It doesn't make sense to have an integer that depends on a continuous variable. So this was an important hint around, in the first 2 decades of the 20th century, which led people in the development of quantum mechanics. Are there any questions on that? Yes.
Just want to emphasize change of time very slowly compared to period, and that remains constant. Just I have the doubt that it's like saying if you move slowly enough, the precision is constant.
Well, it's not the same as saying, I'm not quite sure what analogy you're making there. I mean...
You're saying that if the time is long enough, meaning the change is slow enough, something remains constant.
Yes. Well, for example, if you take a pendulum, you can actually do this experiment. You could take a pendulum, which is oscillating with period 1 second, and you could very slowly change the length of rope defined in your pendulum. The energy will change because you're changing the Hamiltonian, and the frequency will change. But if you lower it slowly enough, they will both change in such a way that the energy over the frequency is constant. And this was the fact that saved quantum mechanics. This is the thing. This is why Bohr was such a clever guy when he said it was the action variable that needs to be quantized when you want to, for example, compute the hydrogen spectrum. Any other questions? Okay, well, this concludes what I wanted to say about adiabatic invariants. Did you guys find a picture? Did you guys find a video of the driven damped pendulum for us to look at? Okay, should we take a look at? So this was your homework assignment. Should we take a look at that? Okay. Okay. Let's see. This will be exciting. Okay, maybe I'll stop the recording because who knows what the hell will happen.